All right, so this is going to be our walkthrough on the homework assignment called logarithmic differentiation. So we want to remember that logarithmic differentiation is what we need to use whenever we have a function that is being raised to the power of another function, right? We can't use the power rule, right? Because the power rule works for a function to the power of some number. And we can't use the exponential rule because that works for some number to the power of a function, right? We cannot use either of these rules. We have to use this new technique called logarithmic differentiation that allows us to take the natural log of both sides of our equation, effectively removing the function that's in the exponent, right? It allows us to bring a function outside of the logarithm in front, right? So we can rewrite this as natural log y is equal to the sine of x times the natural log of x, if we take the ln, the natural log of both sides. Then we just use implicit differentiation to differentiate. We get 1 over dy dx equals, and then for sine x times ln x, we're going to have to use the product rule. So that'll be sine of x times the derivative of ln, which is 1 over x, plus ln x times the derivative of sine, which is cosine x. And then to get our final answer, well, almost our final answer, we have to multiply both sides by y. So we'll have y times sine x over x plus ln x times cosine x. But because we started off with a function that was all in terms of x, we don't want to leave a y in our final answer. So we'll just replace it with what y is. Y is x to the power of sine x. So our final answer here should be x to the power of sine x times sine x over x plus natural log x times cosine x. And that should be our first solution to problem number 1. And again, it's logarithmic differentiation because we start off by taking the log of both sides and then differentiating implicitly. So when we look at this second one, cosine of x to the power of cosine of x, we should immediately recognize that this is a function being raised to the power of another function, which means we need to take the natural log of both sides of this equation. So we're going to have natural log y equals the natural log of cosine of x to the power of cosine of x, which should be rewritten as natural log of y equals the cosine of x times the natural log of the cosine of x, right? We're just going to bring this exponent out in front of our logarithm. Now we can differentiate implicitly. So 1 over y dy dx is what we should get for the natural log y term. And then for the cosine x natural log cosine x term, that's going to be a product rule problem. And you'll note that these are always going to end up being product rules, right? Because we're bringing that exponent out and multiplying it in the front. So it should be the first function, cosine x, times the derivative of the natural log of cosine of x. Well, we'll do that a little bit off to the side, right? Natural log of cosine x is natural log u, with u equal to cosine. Well, the natural log of u is 1 over u, and the derivative of natural log u is 1 over u. And the derivative of cosine x is negative sine of x. Seem to have reached the edge of the board there. I can't seem to fit that on. So we'll move that over. Negative sine of x. So the derivative of natural log of cosine is negative sine, we'll go back to blue here, negative sine of x divided by u, where u was cosine of x. And then we will finish our product rule by adding to that our derivative of our cosine term. Okay. So our derivative of our cosine term should be a negative sine of x. And then our natural log of cosine x should still be there. Right, so we've got first function, cosine, derivative of second function, that's the derivative of natural log of cosine. And then we've got second function, natural log of cosine, and then multiplied by the derivative of the cosine, the negative sign. And now we just do a little bit of simplification here. Our cosines should cancel out. And we've got dy dx. When we multiply by y, we'll recognize that when I multiply by y, I'm multiplying by cosine x to the power of cosine x. So I'm just going to write that y as cosine x to the power of cosine x. That's the y, right? That's this y. Just became cosine x to the cosine x. And then next to it, we've got negative sine x minus sine of x times natural log of the cosine of x. And that should be our final answer for the second problem. For number 3 here, we've got, again, a function being raised to the power of another function. Right, this is y equals the natural log of x to the power of x. So what we'll do is we'll take the natural log of both sides, which allows us to see that x that's in the exponent here can come out into the front. So we end up with the natural log of y is equal to x times the natural log of the natural log of x. And we'll differentiate both sides implicitly. So 1 over y dy dx. And x ln of x is going to be another product rule problem. So it's going to be x times the derivative of the natural log of the natural log of x. So if we do that off to the side here, that's the natural log of u, where u is the natural log of x. Well, the derivative of natural log u is 1 over u, and the derivative of natural log x is 1 over x. So that's 1 over x ln x. So we've now got x times 1 over x ln x. And then we'll add to that the derivative of x, which is 1, times the natural log of the natural log of x. And that's the end of our product rule. Right? We have the first function x times the derivative of the second function. Then we have the second function times the derivative of the first. We can hopefully just see that we can cancel out the x and the x here. And so we end up with dy dx is equal to, when we multiply by the y here, right, when we multiply the y over here, we have to remember that what does y equal? Well, y equals the natural log of x to the power of x. So that's the y. And then next to it, we've got 1 over ln x plus the natural log of the natural log of x. And that should be our derivative there for number 3. For number 4 here, we've got tangent of x to the power of e to the x. So again, this is a function being raised to the power of another function. So we'll take the natural log of both sides. Right? And when we do that, we should see, again, that e to the x can come out into the front, giving us natural log y equals e to the x times the natural log of tangent of x. We'll implicitly differentiate, so the natural log of y becomes 1 over y dy dx. And then the e to the x times the natural log of tangent x should become a chain rule derivative, right? So the e to the x is just e to the x. And then the natural log of tangent x for the product rule there, we'll write that over here as natural log u, where u is tangent x. So it's 1 over u times the derivative of tangent, which is secant squared. So the derivative of natural log of tangent of x is secant squared of x over tangent x, which we'll do a little work probably to simplify that in just a second here. And then plus the derivative of the e to the x is e to the x, and then times natural log of tangent of x. Now we'll bring our y over to the other side. Just like every other time when we bring that y over to the other side, we're going to replace it with our original function. So we have tangent x to the e to the x power, and then times, well, we've got e to the x times secant squared over tangent. So like, let's do a little work off the side here. Secant squared over tangent, right? So secant squared is 1 over cosine squared. And if we put that over tangent, that's over sine x over cosine x. Right? Well, those don't have the same denominator, so I can't exactly just cancel them out. But what I can do is I can, since it's a fraction divided by a fraction, I can just kind of multiply by the reciprocal, right? I can get rid of that and multiply by cosine over sine. And then we should see that one of the cosines in the denominator cancels with the cosine in the numerator, and we end up with 1 over sine x cosine x. So looks like we've got e to the x over sine x cosine x plus e to the x natural log of tangent of x. And if you really want to, you can factor the e to the x out of that, but I don't really need you to do that. That's just up to you. All right, we've got one more here. This would be our first problem where we've used an inverse trig derivative. So you haven't learned the inverse trig derivatives yet. If we haven't done those in class, by the time you see this assignment, well, we're going to do them the very next day. So don't worry about it yet, but you should eventually have the derivative of inverse sine of x memorized, right? And the derivative, I'm going to write it over here. The derivative, just in case I haven't done any videos with it yet. The derivative of inverse sine of x is 1 over root 1 minus x squared. So if you watch the lecture videos, you can see advanced of our class why that's the case. So we proved that in the lecture. But we'll use that derivative here. We're first going to take the natural log of both sides, though, because we see that it's a function to the power of another function. And so that allows us to bring that out into the front. So we have natural log y equals the inverse sine of x times the natural log of x. And so now when we do this implicitly, we'll just first off get 1 over y dy dx. And then that should equal our first function, inverse sine of x, times the derivative of natural log, which is 1 over x. And then we'll add to that the natural log of x times the derivative of inverse sine of x, which is 1 over root 1 minus x squared. And so now our final answer, again, remember that we're going to multiply this y over here, and that y is x to the inverse sine of x. So we've got x to the inverse sine of x times the inverse sine of x over x plus the natural log of x over root 1 minus x squared. And that should be our derivative. And so that's our walkthrough for the assignment called logarithmic differentiation. Remember, logarithmic differentiation is what we should use every time we are taking the derivative of a function being raised to the power of another function. And every time. And that is it.